Hello, my name is Matthias Troyer. I'm a technical fellow and corporate vice president at Microsoft Quantum. We lead the team working on quantum applications and quantum architecture. We've talked a lot about how do we build a system for utility scale, a quantum system that solves a problem where the value of the solution exceeds the cost of the computation. We talked about the applications, the workloads. We talked about the developer tools and resource estimation. We talked about the quantum software. And this time we want to zoom deeper in the stack onto the quantum engine, where we are translating the quantum instructions all the way down to the control signals for the physical qubits. And I want to talk about trade-offs and choices we have to make to reach utility scale. And for that I have to make assumptions. The assumption is I'll choose a machine with 1,000 logical qubits. It starts being interesting at a few hundred, and we want to aim for ones with 10,000 more logical qubits. But let's start today with 1,000 logical qubits. And the clock speed is important as well. We look at slow machines running at the kilohertz, so 1,000 logical instructions in a second, 200 kilohertz, which would be what I would like to have. The typical program then will issue between 1 and 100 instructions per cycle on the 1,000 logical qubits, and might have a few measurements. So with that, we expect between 10 to the 4 and 10 to the 7 instructions per second being sent down from the program in software to the quantum engine, and a few measurements coming back up. That all seems very tractable and feasible. I don't see a challenge in that. The challenges start appearing when I go a bit lower in the stack. So let's look at how the quantum instructions are translated to the specific logical operations of a given QEC code. And here I want to choose an example of the CNOT gate that I'm translating down to the logical qubit operations of a surface code. The surface code for the CNOT needs an ancilla qubit A here, and the CNOT gets translated to a sequence of 4 measurements and joint measurements. I start with the C measurement on the ancilla, then an XX measurement, a CC joint measurement, and then one more X measurement on the ancilla. The measurement results of those 4 measurements are XORed and then used to potentially apply the C polygate on one qubit and the next polygate on the other qubit. So those are the 5 cycles that I would need to translate the CNOT instructions to the surface code operations. But I can further simplify it, because it turns out that I do not have to apply the C and the X gate to the qubit. I can deal with those gates classically in something that is called polyframe tracking. While the X gate flips the 0 and 1 state, and I can apply that to a qubit to flip the qubit, or the C gate flips the phase, so it changes the plus state into the minus state, and vice versa. So I can either apply these gates to my qubits, or I can do what is called polyframe tracking. There I simply swap the labels. I just keep track that I've swapped 0 and 1 in software, or simply keep track that I've swapped plus and minus in software. I don't have to actually touch the qubit. I don't have to update the state of the qubit. I can just keep track of how the labels have changed. Now, that's good news because it means I don't have to do those quantum gates. But it poses a new challenge because now the CNOT gate, which was a unitary gate that had no result, now turns into 4 measurements and sends back 4 measurement results. And depending on those results, I have to keep track of my polyframes. That means now suddenly, instead of having just a few measurements a second, I have to deal with between 100,000 and 100 million measurements a second in software. And that gets really hard and challenging. What we thus would like to do is to hide that from the user. I don't want to return all those measurements to the program. And I want to handle the polyframe tracking, all of the processing, all of the label updatings in the quantum engine. So that to the user, it seems that I'm just performing the unitary CNOT gate. There's no measurement result returned. The measurements are processed classically in the quantum engine. This is one reason why we wanted to introduce a quantum instructions set architecture that is higher level than the specific quantum error correcting code. We said to make the programs we do hardware and QEC code agnostic. We also introduced an instructions set architecture to abstract the instructions beyond the specific logical qubit operations. But more importantly, as we see here, doing that allows us to optimize performance, allows us to simplify the software, allows us to balance the instruction richness with execution speed and simplicity. Let us now go even deeper from logical qubit operations to the physical ones. And there, the first question is, how many physical instructions will I have to issue? And how many measurements will I get back? For that, let us recall the overhead of quantum error correction. We have a logical error rate depending on the physical one and the code distance d. Then, based on the code distance, we can calculate the number of the physical qubits we need per logical qubits. And we calculate the logical cycle time as a function of the physical cycle times. And with that, we can now calculate the overhead, how many instructions do I have at the physical level compared to the logical level. And that is the product of the space overhead and the time overhead. The space overhead is the physical qubits divided by the logical qubits. That's a factor 100 to 1,000 typically. The time overhead is the ratio of the logical to the physical cycle time. There's a factor 10 to 100. So the overall the ratio is a factor 100 to 100,000. With that now, the number of control instructions we have is between 10 to the 9 and 10 to the 13. The number of measurements that I get back is between 10 to the 8 and 10 to the 13. That means I have between 1 billion and more than 1 trillion instructions per second. The immediate consequence is it will be very hard, if not impossible, to do that in software. So these control operations we expect have to be done in hardware. I need to harden the qubit control. That means I also have to harden the mapping of logical operations to physical operations. It has to be done in hardware. And then even these numbers seem daunting, but that is the challenge we face. So let us now take a step further. Many qubit types require to be cooled to millikelvin temperatures. So let us think a bit about that challenge. For a fast machine, I have to issue somewhere between 10 to the 11 and 10 to the 13 instructions per second, and have to do, depending on the type of qubit and the quantum error correcting code, between 10 to the 10 and 10 to the 13 measurements a second. If in the code I get to cool maybe about a watt of power, maybe only a milliwatt in that range, then doing 10 to the 13 measurements a second means I don't have more than a few femtojoule per measurement. That's not much energy that I can use here. And it's simply not possible to send up 10 terabit a second with just less than a watt of power. We don't have the technology. Hence, the solution is to send the analog readout signal up from the qubits to room temperature, to amplify the signal, bring it up to room temperature, and then to process the measurement signals at room temperature. That makes things much easier, but it also has an impact on the architecture and the time I have, the latency for feedback. How about control? Sending down 10 to the 11 to 10 to the 13 physical operations per second, which might be 1 to 100 terabit a second, will just heat the qubits far too much. I just cannot sustain that. Hence, the idea is to send only the logical operations down. And logical operations, we had about 1 million to 100 million, so I'm sending down not more than a gigabit a second. That is totally feasible. But then I have to convert these logical operations in the cryostat at low temperatures from logical operations to physical ones, going then from the 10 to the 8 logical operations to up to 10 to the 13 physical ones. We can do that with cryocontrol. But even that may be challenging for some qubits, and that's why one can then split the machine into many smaller machines to cope with the bandwidth and the control requirements. That eases the control and readout, but it will increase the cost. And next time we'll look at these trade-offs. What we've seen today is that if we choose the quantum instructions set wisely, software control at the logic level will not be a problem. Encoding the logical instructions into the physical one, doing the polyframe tracking, and then the encoding into the physical qubit operations will have to be hardened. And the biggest challenge will be not making the qubit. The biggest challenge looking at those numbers will be how they deal with the number of measurements and the control I need for utility scale. And we'll talk about that next time. Thank you.